Oh, wonderful. Beautiful. Look at this microphone here. Okay, so this is the talk you get if you say, with 30 seconds notice, I want to talk, okay? So I'll just wander up and down and malign people left and right, and, you can throw tomatoes. It'll be entertainment. So I was going to do a lightning talk on this, but I'll stretch it out a bit. Basically, one of the real problems that I get at conferences is that people like to encourage me, They like to build me up. They come up to me and they say encouraging things like, how is it that OpenOffice, can't render its splash screen in the time that Numeric can start up entirely, So this is a good question, and, I often ponder these kind of things myself at night. So I go away, and I say thank you, what a lovely comment, And so just to tell you, some of the things that we've done to speed up OpenOffice, actually, this so hurt me inside, that we wrote our very own splash screen application for OpenOffice. It's actually a separate program, and it renders the splash screen far faster than anything else is ever going to. So, it's pretty neat. But this actually helps a lot in several ways. It's a nice factory process thing. So we're speeding up OpenOffice a lot. Also done a whole load of optimization on linking and some of the really core, system brokenness that means that unfortunately C++ is particularly slow and inefficient on Linux. So we're trying to improve some of these things. And this is good. But at the end of the day, having done all of this work, you discover that actually you're still optimizing the 20%. So I have a little drawing down here. I don't know if you can see the complicated pointing technology here. So the CPU time, as you see, for what users perceive as a startup of OpenOffice is now only 20%. We can shrink that down to 10%, but this is not a big win. So I've spent quite a lot of time recently looking at the other 80%. And the other 80% is very interesting because it's all I.O. time. And it's of course, easy to blame an application for doing I.O., right? It's clearly the application's fault, right? If it didn't do any I.O., it would be quick, right? Obvious, huh? Just don't do any I.O., right? Well, so this is the kind of kernel people's attitude, unfortunately. So one has to sit down and explain to the kernel people that, we're trying quite hard not to do I.O. We've done all these beautiful things. So, for example, we used to store our configuration in OpenOffice in this nice XML files, sort of they're kind of flat and you can read them and there's lots of them and isn't it beautiful, Remind anyone of gconf, huh? Yeah. Anyway, so isn't this perfect? Unfortunately, the cost of actually loading these things and seeking all over the disk and then, getting them in, it's a huge I.O. cost to this. So the solution, of course, instead of fixing the file system or addressing this problem at root, is to ram them all into some massive, ugly binary database, right? Yes, now we have just one file, and unfortunately, we've kind of lost a whole load of the nice benefits. So you start explaining these things to kernel people, and incidentally, this pie chart here is very, very reliable. It's very easy to measure. All you do is you measure the warm start time, and you measure the cold start time, and you take the difference, and this gives you that graph. It sounds easy, huh? Right. And it often comes out to sort of 20–80%, but the problem is with measuring cold start time that even if you power your machine off and strip out all of those beautiful Beagle indexers and all these other things, good things that do I.O., and you have loads of memory, so you're not going to swap at all, and you turn every daemon off and you boot only raw X, and then you start just your one application, and you time it, you pretty soon discover that you get a plus or minus 10% variation in the cold start time. So there's just this massive error bar on it. And of course you can reboot your machine hundreds of times and run the program hundreds of times and get lots and lots of measurements. But if your cold start time is not too good in the first place, this is going to take a long time. And in fact, Quaylon, sitting in the front here, is a hero, and he's been doing this for OpenOffice at some considerable length. But I was listening to the Pango talk the other day, actually Pango Cairo, and the talk of all these 3%, 5% gains that add up to something worth having. And you just can never see them in the noise with I.O. So I have a pretty picture that shows my potential solution to this. And this I've done a whole load of work with Federico doing some of the beautiful graphics that hopefully we'll show you in a sec. And the idea is then to get a deterministic number, right? The number can be really, really broken. And incidentally, if you use kcache grind, who's used kcache grind? I don't use any KDFs except kcache grind is just amazing. It rocks my world. But when you actually talk to the Valgrind authors, they sort of giggle, when you mention that actually you're using their, call cycle estimation thing. Because the cycle estimation in K-cache grind, though very, very useful, is a total guess. It's just sort of they tried, right? And it's made up of magic numbers, multiplications by cache misses, and so on and so on. But it's really useful, right? And it doesn't matter that it's, this pseudo CPU that's never existed. It's actually really useful. So the theory is that we then get a deterministic measurement of all of the I/O that's being done by an application, and we store a little trace file here. So we then know exactly what, say, gedit does at startup. And then we have this simulator thing, and that also takes a snapshot of the disk, so its exact layout, where everything is, where the inodes are. And we also take a thing called disk sim or some equivalent that sort of models a modern hard disk, which it's kind of easy to do. And you throw all of these things together, and you can simulate how slow it will be. And the punchline is that out of this thing, you can get lots of information, but the most important information is one number. How long did it take, right? It took 30 seconds. Last time it took 35 seconds. This is a big improvement, right? And maybe it's not exactly that win on your hardware, with your amount of memory, with your swap, setup or whatever, your file system. But at least it's a win. You went the right direction, right? And previously that's been very, very difficult to work out. The other nice thing is that I'm fairly convinced, having talked to a number of people, that most of the problems are not in the application space. Yes, of course, there are some really stupid things going on, and some people create millions of little files, but at the end of the day, I think a lot of the problems are someone else's fault. So, I'm just trying to build evidence so that we can persuade them that this is the case. And one of the problems with kernel hackers is that, and I love kernel hackers, they're just wonderful. They provided this excellent kernel, but they're obsessed by CPU cycles, If you can shave one CPU cycle off get time of day, you're a hero in the Linux community. Get time of day, and it's now quicker. We can call even more of them in an hour. That's wonderful. But the problem is that actually, if you save one seek during OpenOffice startup, I think we do something like 14,000 system calls on OpenOffice startup, which kernel people claim is a catastrophic performance problem, though it never shows on any profiles. If you save one seek during all of OpenOffice startup, something like hundreds of ticks per system call that you save, and it's just like an impossible saving. So anyway, we want to persuade them that their life is going to be easier with us. We'll shut up and go away if they fix the problems. So I'd like to show you here in my carefully prepared, beautiful graphical presentation thing some of the trace data I've got here. Actually, just a gedit thing, and you can see as it starts up, we can start to see interesting things. So inodes being read, block I/O happening, and we flatten it all to file names. So you can see here. M, it means a memory map happened in this range of that file, mapped twice because of various protection reasons and so on. And so one of the things you see, stack trace information coming out, you see things like this L guy happening. And so you can see that a load was done from that page. So this page was touched once from there, and actually happened in memset. Actually, I think the store probably happened in memset. So you can also see when a page was dirtied the first time, so you can start to build working set information and see what's actually happening. And as you go on, you see that really there's a whole lot of stuff just going on. So that's not very interesting. And then you see this beautiful mono. Okay, let's try putting this. Okay. I must point out that most of the graphical beauty is Federico Mena's, Mena's fault, and it's kind of saturated here. But anyway, so here you see, sort of, I guess, a little histogram, a bit like K-cache grind. You also see the stack information on the left has got horribly corrupted at some stage. But let's dive down into something so we can't see that. So you look at this guy here, and this is a whole load of, I guess, read no cancels. I don't know why they're not all the same one. This is coming out of fontconfig, doing a whole load of work at startup. So there's a whole load of things I have to say about this. First of all, the numbers are totally meaningless at the moment because our file system model is not yet plugged in. The balance between implicit I/O, as in touching memory maps that you've never been able to see before, and explicit I/O is also mangled. But you get the idea that you can see exactly what functions caused what I/O to happen where, which is good. And you can also see, I guess, the opposite thing for when we all move to our flash filing systems and we have no seek time at all, and yet the bandwidth is fairly low. You can see where the cost will be of getting all that stuff. So that's quite nice. You can also see it in terms of the file system, where it is, where is all the bad stuff happening. And you'll see there's quite a lot of shared libraries here. So I guess that would be most applicable to a really cold start, like when you log in or something like that, login time, because normally most of these libraries will be mapped. Okay, so that most of this data will be there. It's pretty easy to fix that. We just need to run a sort of sample application first to warm the caches and then really start doing the measurement. So that's coming along. We can also see an address view. Actually, this is kind of confusing like that, so we can expand it a bit. And so you can start to see, I don't know if you can see the little black dots. Do they look like? Good. So as I was sitting in the back thinking, for my lightning talk, I need to hack up, the working set algorithm, which is unfortunately still half finished. These are initial page touches here. So you can see, for example, all these libraries are mapped chronologically. Just for those who can't see graphs instantly, this thing here is time on this axis, and this is address space on this axis. So you can see, that these guys are all mapped, and then they start doing initializations, and then they peel back and do some more. But some of these things are pretty scattered. So if you come down here, something I pressed quite hard for, the icon data cache. So this, I think, is the Tango icon theme. And the beautiful thing about GNOME, one of the really good things, is that we have all of the icon data in a nice memory map file, and you just pass that data straight through to GTK, and it renders it to the X server. So it's really efficient, which is excellent, because other people like to load the open icon in every single application, and then copy it and have all of these terrible memory wastage problems from it. But maybe what you can't see here is that this huge block of icon data is being accessed essentially at random all over the place. And it's sort of 150 meg big, something like that. So one instantly easy to do fix here is simply to sort your icons into something like an order that they might be used in. Group icons that are likely to be used together, because it sure seems that most of it is never used, right? For most applications. So yeah, just a simple sort algorithm here, and we'll not only shrink our working set drastically, but also improve startup performance. So I don't know, am I running out of time? How long was I supposed to ramble for? Aha, someone's coming to my rescue. Has this lady arrived yet? Okay, well, I'm pretty much done, so you better try finding some other sap to come and entertain the masses. Or we could send some lions in. That's pretty good. Yeah, it looks fun. Is there any questions that anyone has? Is there anything I'm missing? Is there anything I should be doing? This gentleman in the stripy shirt. Ah, yes, you see. So it's such a cool tool that we've been hiding it carefully. Yeah. Also, it's not finished, as I've happened to mention. And were you to use it on your application today, you would see a lot of interesting things, none of which bore any relation to reality, which might be a bad start. I mean, yeah, you're welcome to optimize my very, very broken view of how file systems work. But yeah, I think in the next few weeks, actually, I also forgot to mention this is, in theory, a collaboration between AMD and Novell. So actually, AMD are supporting this work. So it's kind of this excellent thing. Do you want to hack on it? If you want to hack on it, you're my friend. I'll give you the Git URI. Use. Yeah, I know people that want to use it. I know lots of them. That's cool. So yeah, we really want to do it for OpenOffice. Let me show you just one more. I wonder if I can get the Nautilus one. I was really pleased with this because I thought, this profile is actually 10 times bigger than the biggest one we've tested with, and maybe there'll be all these memory and scalability issues, and hey, we're using mono after all, and there's a GC, and then it just turned out not to be an issue at all. Just worked fine. So I'm pretty pleased. But yeah, so you see, and one of the things that you also see is this guy here, this do lookup X. The linking is really quite a large chunk of random access pattern dotting all over the memory. But hopefully that's coming under control a bit. Any other questions? You're in a questioning mood. Yes? Yeah, right. So well, I'm doing a proper talk at the Linux conference in Cambridge in September, and my hope would be that by then I'd actually have something persuasive I can say to kernel people, look, when I swap this I/O system, this file system image round, having done this little tweak, because of course you can plug lots of different images in and you can compare different file system layouts very quickly, then I get this massive performance win, you know? So hey, why don't you do this little tweak here? Or, you know, so yeah, I mean, in terms of future development, so I hope to have a release by September, you know. But if you want to hack, it'll be much quicker, you know. I mean, it really is just me and my, you know, spare time, really. So yeah, I mean, I guess that's the other thing that you miss here, that it not only helps the application, it can help the kernel space. And you talk to people like Andrew Morton, you mention your horrendous I/O-related problems, and he nods his head and, yeah, no, that's interesting. Actually, we've no idea, you know, how to optimize the VM because, well, we just try and stop it doing stupid things, you know? We just kind of, yeah, no one really knows how it works either, sort of thing, you know, and what its performance characteristics are, and, you know, well, we just try and do our best. But there's no regression tests, there's no idea of what, say, an Oracle database does to a Linux kernel, or what a desktop application does to it, or what, you know, what we even want to happen in terms of big server and big client workloads. So, I mean, my pipe dream in the, you know, sort of 10,000-year time frame is, you know, that we can simulate a huge amount of the kernel and improve things like VM performance. I mean, I don't know if you've ever, you know, killed Nautilus and seen the X resource that hides behind the Nautilus root window. Does that ever happen to you? And you see it draw like this. It goes, and your hard disk makes this wonderful noise at the same time. And the reason is that you have here a perfectly flat, contiguous piece of memory that has been forced out to disk over a long period, and you discover that all of these blocks appear to be way away from each other on disk, and they're paged in one by one, and you can count, you know, I mean, you can see it happen. And that's pretty bad. It's pretty embarrassing, I think. And also, when you ask about the VM algorithms, it seems, you know, last time I checked, there's not even sorting by virtual memory address. So, I mean, you can bet that many algorithms walk linearly through memory, and so it might be a good idea to page these things out, you know, in some linear order on disk, but there's no even attempt to sort the unused list by that. And the problem is, of course, it's very hard to prove this is a performance benefit. You know, you can't, it's just difficult to show, and it's difficult to demonstrate to people, and so they don't want to change something that works, you know? And you can understand that, so I just want to show them, look, there are easy wins, you know? Sorry, gentleman here can contradict me. Yes. QEMU?
Yeah.
Mm-hmm. Yeah. So there's kind of two meanings of emulation. I probably should use simulation, because really, you know, I'm not making an operating system emulator, or it's not a VMware thing. I just want two numbers back, really, you know, how long did it take to get the block, and, you know, well, how much did you read, I guess. But basically, I just want a time back. And so, you know, you notice that we can start Nautilus up and simulate everything in a second, whereas it really takes 15 seconds to start. And, you know, so the idea would be but you could have huge workloads that you can run that you couldn't run in many days, but you can simulate them in, you know, 5 minutes and say, ha, all known workloads got quicker. Or, you know, only 1% of workloads, and these ones got a bit slower with this, but, you know, 90% got faster. Let's do this tweak.
I was just thinking that you could have the whole system,
Mm-hmm.
emulate the whole system,
Uh-huh.
and you would get all the blocks that are in when they are in, and because then whole system emulation might be the best.
Yeah, you could do that. It's entirely possible to do that sort of thing. I think what I'm interested in is getting the file system snapshots and pulling that out, you know, so I want to pull a lot of bits into it. But yeah, I mean, if there's a good way to do it, reusing code, I'm always eager to do that. My feeling is that something simple and light that you can install everywhere and it's not, you know, bloated. The other thing is that you can do some of these things with system tap. You know, you can see all the blocks that were read and so on and so on, but it's not deterministic. At some level, you know, threading changes and different race conditions and different file system layouts, you know, will give you just very different numbers, and it's very difficult to compare them. And yeah, I don't want people to be recompiling their kernel. That's the other thing. It's been years since I recompiled my kernel, and frankly, I hate it now. I used to love it, you know, all those options, isn't it great? But it just means that you inevitably break something when you recompile your kernel, it seems, nowadays. And, you know, I'd rather not, oh, well, just apply this patch to your kernel, reboot, and rerun your application, because this is not nice. You know, I'd rather just, aha, this is the theoretical tweak. You know, I've done it. It makes everything faster. Now go and implement it in your, you know, your big old beast of a kernel. So, cool. One more at the back there. Yeah. Yep. Yeah, dtrace. So dtrace solves part of the problem, which is that you can see what happened on that one operating system with that one file system layout with that one disk geometry once. That's fine. And so you can measure those things, and that's true. And you could use it instead of Valgrind to produce a trace of an application. Absolutely. Yeah, completely agree with that. I think it's hard to replace the simulation aspect if you want to try lots of different file system geometries. You want to try lots of different applications, and simulate them very, very quickly to see the effect of a change that you've made. But yeah, I love dtrace as much as the next guy if it's free software. So that's cool. Excellent. I think that's about it. Can I? Thank you. You let me off the hook.